In 1953, before the first satellite had even left Earth, humanity imagined what it would mean for something from beyond our solar system to arrive, and now, that story may no longer be fiction. You've been following 3 Atlas. You know it's the third interstellar visitor. You know it's massive, fast, and weird. But what you might not know is that the new data might change everything. The numbers have been coming in for months now. Observatories across the planet, space telescopes orbiting in the dark, amateur astronomers with backyard equipment pointed at the same coordinates, all of them tracking this object as it falls inward toward the Sunday. The data streams in, gets compiled, gets analyzed, and somewhere in those numbers, in the trajectories and the velocities and the strange absence of what should be there, something doesn't add up. Something that suggests this visitor might not be leaving after all. October 29th. Remember that date. On that day, 3 Atlas will reach perihelion, its closest approach to the Sun, just 1.36 astronomical units from our star closer than Earth, not quite as close as Mars. For most comets, for most objects falling through our solar system on hyperbolic trajectories, perihelion is the moment of maximum velocity, the instant when the Sun's gravity has pulled them to their fastest speed before they slingshot back out into the dark. It's the turning point. The moment of no return, quite literally, because after perihelion, these objects should accelerate away, climb back out of the Sun's gravity well, and disappear into interstellar space forever. Should. That word carries weight now, because the new data suggests that 3 Atlas might not follow the script, might not do what interstellar objects are supposed to do, might, instead, do something that would rewrite every assumption we have about what's possible out there in the void between stars. Here's what we know. 3 Atlas was discovered on July 1st, 2025, by the Asteroid Terrestrial Impact Last Alert System in Chile. A routine survey scan, one of thousands conducted every night, flagging objects that move against the background stars. This one moved fast. Too fast for a main belt asteroid, too fast for most comets. When astronomers calculated its orbit, when they traced the trajectory backward and forward through time, they found something remarkable. The orbit was hyperbolic. The eccentricity, the parameter that describes how elongated an orbit is, came out to 6.137. Any eccentricity above 1 means the orbit is open, unbound, a one-way trip. An eccentricity of 6.137 means the trajectory is essentially a straight line, barely curved by the Sun's gravity at all. It means this object came from somewhere else and was on its way to somewhere else, just passing through. Except that's where the story starts to unravel. The object entered our solar system with a velocity relative to the Sun of 58 kilometers per second. That's its hyperbolic excess velocity, the speed it would have if it were infinitely far from the Sun, where gravity no longer matters. As it falls inward, the Sun's gravity pulls it faster. Basic physics, basic orbital mechanics. By the time it reaches perihelion, it will be traveling at 68 kilometers per second relative to the Sun, faster than almost any natural object we've ever observed moving through our cosmic neighborhood. And then, according to every model, every equation, every prediction based on centuries of celestial mechanics, it should swing around the Sun and head back out, slowing as it climbs against gravity's pull until it reaches its original 58 kilometers per second escape velocity and leaves our solar system forever. Should. But what if it doesn't? Avi Loeb has been asking that question since early July. Loeb, the Frank B. Baird Jr., professor of science at Harvard, the founding director of Harvard's Black Hole Initiative, former chair of the astronomy department, a man whose career has been built on asking uncomfortable questions and following data wherever it leads, even when it leads to places most scientists don't want to go. He's been tracking 3 Atlas since discovery, writing paper after paper, blog post after blog post, analyzing every piece of data that comes in from telescopes around the world. And what he's found has made him give 3 Atlas a ranking of 4 out of 10 on what he calls the Loeb scale, a metric he developed to quantify how likely an object might be of technological origin rather than natural. 4 out of 10 doesn't sound high. It's not saying this is definitely artificial, but in the context of interstellar objects, in the realm of things that have traveled from other star systems across light years of void, 4 out of 10 is extraordinary. It's higher than Oumuamua, the first interstellar object ever detected, which he ranked at 3. It's based on 8 separate anomalies, 8 characteristics of 3 Atlas that don't fit the expected profile for a natural comet or asteroid. Let me walk you through them slowly, because each one, taken alone, might be explained away, but together they form a pattern that whispers of something we might not be ready to accept. First, the trajectory alignment. 3. Atlas is moving on a path that's nearly aligned with the ecliptic plane, the flat disk where Earth and the other planets orbit the Sunday. Most interstellar objects should arrive from random directions because space is 3-dimensional and stars in the galaxy move in all directions with relatively similar velocity dispersions. The probability that an interstellar object would randomly align within 5 degrees of the ecliptic is about 0.2%, 0.2%, 1 in 500. Oumuamua arrived at an inclination of 123 degrees to the ecliptic. Borisov, the second interstellar visitor, came in at 44 degrees. 3 Atlas, 5 degrees. Almost perfectly aligned with the plane where all the planets orbit, where all the targets of interest in our solar system happen to be located. A coincidence? Maybe, or maybe not. Second, the sunward jet. In July and August, when Hubble and other telescopes imaged 3 Atlas, they saw something strange in the coma, the cloud of gas and dust surrounding the nucleus. There was a plume extending toward the sun, not away from it. Comets develop tails that point away from the sun because solar radiation and the solar wind push the gas and dust outward. That's basic comet behavior, documented thousands of times. But 3 Atlas showed material concentrated on the sun-facing side, extending in the direction of the sun rather than away from it. Some researchers argued this could be explained by the viewing geometry, by the angle at which we're seeing the comet. But detailed analysis by Loeb and his colleague Eric Quito showed that even accounting for the viewing angle, the sunward extension is real. It's not an optical illusion. It's actual material preferentially moving toward the sun, which is unusual, which doesn't match what comets are supposed to do. Third, the mass. In September, Loeb and his collaborators, Richard Clowett and Peter Veris, published a paper analyzing the trajectory of 3 Atlas over several months, from May 15th through September 23rd, using over 4,000 astrometric observations from 227 observatories worldwide. They were looking for non-gravitational acceleration, any deviation from a purely gravitational trajectory that would indicate the object is being pushed by forces other than gravity. Comets typically show non-gravitational acceleration because they're outgassing, jetting material into space, and that jetting creates a rocket effect that can nudge the orbit slightly. The data for 3 Atlas showed nothing. No detectable non-gravitational acceleration. The residuals between the observed position and the predicted gravitational-only trajectory were consistent with 0. That sounds boring, right? No deviation means it's following a normal gravitational path, just a rock falling through space under the influence of the sun's gravity. Except here's the thing. 3 Atlas is outgassing. We know it is. The James Webb Space Telescope observed it in August and detected massive amounts of carbon dioxide vapor in the coma, gas streaming off the surface at a rate of about 70 kilograms per second. That outgassing should create a rocket effect. It should push the comet, however slightly. The fact that there's no detectable push means the object has to be extremely massive, massive enough that 70 kilograms per second of escaping gas doesn't noticeably affect its trajectory. The calculation is straightforward. Given the upper limit on non-gravitational acceleration from the trajectory data, and given the mass loss rate and outflow velocity measured by Webb, you can calculate the minimum mass of the nucleus. The answer comes out to 33 billion tons. 33 trillion kilograms. At typical cometary density, about half the density of water, a mixture of ice and rock and dust that implies a nucleus diameter of at least 5 kilometers. 5 kilometers of solid icy rock, a mountain flying through space at 58 kilometers per second. That makes 3 Atlas about 1,000,000 times more massive than Oumuamua and 1,000 times more massive than Borisov. It's not just bigger than the previous interstellar objects, it's orders of magnitude bigger, and that raises a question that Loeb has been emphasizing repeatedly. Why? Why would the third interstellar object we detect be so much more massive than the first two? Interstellar objects are created when comets and asteroids get ejected from their home planetary systems, usually by gravitational encounters with giant planets. The smaller an object is, the more easily it gets ejected. So there should be far more small interstellar objects than large ones. The population distribution should follow a power law, with numbers increasing steeply as size decreases. Based on the detection of Oumuamua, which was maybe a few hundred meters across, and Borisov, maybe half a kilometer, we should have detected tens of thousands or even hundreds of thousands of small interstellar objects before finding something as massive as 3 Atlas. The statistics don't work. The probability is vanishingly small. Less than 1/10 of 1%, according to Loeb's calculations. It's as if we rolled dice and got snake eyes 3 times in a row. Possible, but suspicious. Suggesting maybe the dice are loaded. Suggesting maybe 3 Atlas didn't arrive here by the same random process that brought us Oumuamua and Borisov. Fourth, the timing and the close approaches. When you trace 3 Atlas's path through the inner solar system, it passes remarkably close to multiple planets. On October 3rd, it came within 30 million kilometers of Mars. On November 3rd, it will pass 97 million kilometers from Venus. On March 16th, 2026, it will pass 54 million kilometers from Jupiter. And on December 19th, 2025, it will reach its closest approach to Earth, 269 million kilometers, about 1.8 astronomical units. None of these are collision trajectories. None of them are dangerous. But statistically, the probability that a randomly arriving interstellar object would pass so close to so many major planets is extremely low. Loeb calculates it at less than 5,000ths of 1%, 0.005%. It's as if the trajectory was designed to sample the inner solar system to make flybys of all the major worlds. Again, possible by pure chance, but suspicious. 5th through 8th. The chemical and physical anomalies. The lack of water vapor in early spectroscopic observations despite clear evidence of a dust coma. The detection of nickel vapor but not iron vapor in the coma, suggesting unusual dust composition or processing. The green color that appeared during the September 7th lunar eclipse, indicating cyanide emission but not the usual diatomic carbon that causes green comets. The extreme enrichment in carbon dioxide over water, 7.6 parts CO2 for every part water, higher than any comet we've seen before. Each of these can potentially be explained by some combination of unusual formation conditions, unusual composition, unusual heating, or radiation processing. But together, all of them at once in the same object, it starts to feel like too many coincidences stacked on top of each other. And here's where it gets strange, because what Loeb has been pointing out, what the numbers are starting to whisper, is that if you wanted to design a trajectory to visit the inner solar system, to make close approaches to planets, to position yourself for potential gravitational captures or orbital changes or other things, the orbit of 3 Atlas is nearly optimal. The retrograde motion that's moving in the opposite direction from the planet's orbits means that relative velocities during encounters are high which could be advantageous for certain types of gravitational assists or for deploying smaller probes that could use the planet's gravity wells to alter their own trajectories. The low inclination means it stays near the ecliptic where all the planets are, maximizing opportunities for encounters. The timing brings it to perihelion on October 29th, just 8 days after it reaches solar conjunction on October 21st, the moment when it's exactly on the opposite side of the Sun from Earth, hidden from view by our star's glare. That timing is important, because there's a maneuver in astronautics called the Oberth effect. It's a principle of rocket propulsion that says the most efficient time to change your velocity is when you're moving fastest when your kinetic energy is highest. A given thrust applied at high velocity produces a larger change in total energy than the same thrust applied at low velocity. For a spacecraft entering a solar system, perihelion is the optimal location to perform what's called a braking burn, firing engines to slow down, to shed velocity, to transition from a hyperbolic escape trajectory to an elliptical captured trajectory that stays bound to the star. If you were an interstellar spacecraft approaching the Sun and you wanted to become captured into solar orbit, rather than flying through and leaving forever, perihelion is exactly where you'd perform that burn. And if you wanted to do it without being observed, you'd time it to occur during solar conjunction, when Earth-based telescopes can't see you because the Sun is in the way. The geometry is almost perfect. 3 Atlas reaches solar conjunction on October 21st. It reaches perihelion on October 29th. For that entire period, roughly October 15th through November 10th, it's unobservable from Earth because it's too close to the Sun in the sky. If anything were going to happen, if any maneuver were going to occur, that would be the window to do it unseen. Loeb has been saying this repeatedly in his blog posts and interviews. October 29th, mark that date, because that's the key test. If 3 Atlas is a natural comet, it will follow its predicted trajectory, swing around the Sun at 68 kilometers per second, begin the long climb back out into interstellar space, and disappear from our solar system over the next few years as it races away at its escape velocity of 58 kilometers per second. We'll see it again in early December when it emerges from behind the Sun, and we'll track it through 2026 as it passes Jupiter and continues outward. The trajectory will match the predictions. The orbital elements won't change. It will behave exactly as an object on a hyperbolic orbit should behave. But if something else is happening, if 3 Atlas is not entirely natural, if there's technology involved, if there's any kind of propulsion or maneuvering capability, then when it emerges in December, the trajectory might be different. The velocity might be slower. The eccentricity might be reduced below 1, meaning the orbit has become closed, elliptical, bound to the Sunday. It might release objects, smaller craft, probes, debris, something that wasn't there before. We won't know until we can observe it again. Until the Sun moves out of the way and our telescopes can see what happened during those hidden weeks. The silence of space hangs over this question, the waiting, the not knowing. Let's step back for a moment. Let's contextualize this. 1953. The year War of the Worlds was released as a film, the Technicolor adaptation of H.G. Wells's novel about Martian invaders arriving in metal cylinders that crash land on Earth. The film captured Cold War anxieties, fears of invasion, fears of the unknown arriving from the sky. At the time, we had not yet launched a satellite. Sputnik wouldn't fly until 1957. We had no presence in space, no way to detect incoming objects. No planetary defense, no asteroid surveys, no network of telescopes scanning the sky every night. If something had arrived from another star in 1953, we wouldn't have seen it coming. We wouldn't have known until it was already here. 72 years later, we have detection capabilities our predecessors couldn't have imagined. Survey telescopes that scan the entire visible sky every few nights. Space-based observatories operating at wavelengths the atmosphere blocks. Automated systems that flag anything that moves, anything unusual, anything that shouldn't be there. We found 3 Atlas when it was 420 million miles from the Sun, months before perihelion, giving us time to turn our most powerful instruments toward it. We've gathered more data on this single interstellar object than we were able to gather on the previous 2 combined. We have spectra, we have imaging, we have astrometry precise enough to detect orbital deviations measured in fractions of an arc-second. We can track this object's motion through space with incredible accuracy. And yet, despite all that capability, despite all that data, we still don't know what it is. We still can't say for certain whether it's just a comet, an unusual comet, a comet with strange properties, but fundamentally a natural chunk of ice and rock following natural laws through natural space, or whether it's something more. Something that would force us to confront the possibility that we're not alone, that intelligence exists elsewhere, that artifacts from other civilizations can and do cross the vast distances between stars. Most scientists lean toward the natural explanation. 3 Atlas looks like a comet in many ways. It has a coma. It's outgassing. The spectroscopy shows molecules we expect from sublimating ices: carbon dioxide, water, carbon monoxide. It's behaving, in broad strokes, the way comets behave. Tom Statler, NASA's lead scientist for solar system small bodies, told reporters in September that it looks like a comet. It does comet things. It very, very strongly resembles in just about every way the comets that we know. He acknowledged that it has some interesting properties that are a little bit different from our solar system comets, but concluded that it's a comet nonetheless. And he's probably right. Probably. The baseline assumption, the null hypothesis, is that any object we find in space is natural unless proven otherwise. We've never detected a confirmed artifact of extraterrestrial technology. We've been doing SETI for over 60 years with no confirmed signals. We found no evidence of intelligent life beyond Earth. So, the prior probability, the probability before considering the specific evidence of 3 Atlas, is that it's natural. That's just Bayesian reasoning. Start with what's most likely based on past experience, then update based on new evidence. But Loeb argues that the new evidence should shift our probability assessment, should make us less confident in the natural explanation, more open to alternatives. He's not claiming certainty. He's not saying 3 Atlas is definitely artificial. He's saying there's maybe a 30 to 40% chance, based on the anomalies, based on the statistics, based on the patterns that don't quite fit. 30 to 40% isn't high enough to be sure, but it's high enough to pay attention, high enough to watch carefully, high enough that if something unexpected happens at perihelion, we shouldn't be entirely surprised. The question of gravitational capture sits at the heart of this, because that's the scenario that would most dramatically change our understanding. If 3 Atlas were to slow down during perihelion passage, if its velocity were to drop below escape velocity, it would no longer be on a hyperbolic trajectory leaving the solar system. It would be on an elliptical orbit that stays bound to the Sun, orbiting indefinitely, like a comet from the Oort cloud. It would, effectively, become a permanent resident of our solar system rather than a temporary visitor. For a natural object, this is essentially impossible without outside intervention. The orbital energy is determined by the velocity and position. At perihelion, 3 Atlas will have a specific kinetic energy dictated by its approach velocity and the Sun's gravitational potential at that distance. To become captured, it would need to lose a substantial amount of that kinetic energy, hundreds of gigajoules per kilogram. The only natural mechanism that could remove that much energy would be a collision with a planet or an extremely close pass through a planetary atmosphere that creates drag. Neither is going to happen. 3 Atlas isn't passing close enough to any planet for those effects to matter. So if it slows down, if the post-perihelion velocity is measurably less than the predicted 68 kilometers per second, that would indicate non-gravitational forces acting on the object. Outgassing can do this if the jetting is in the right direction, but as we've seen, 3 Atlas shows no detectable non-gravitational acceleration from outgassing in the pre-perihelion data. For outgassing to suddenly slow it down enough to capture it would require an enormous sustained jet in exactly the right direction, which seems unlikely. That leaves other possibilities. Artificial propulsion, a braking burn, an engine firing at perihelion to shed velocity, the Oberth maneuver that Loeb keeps mentioning. Or it could release smaller objects that perform their own maneuvers. Loeb has suggested this repeatedly. If 3 Atlas is a mothership, it might continue on its hyperbolic trajectory, but deploy smaller probes at perihelion. Those probes could use their own propulsion combined with gravitational assists from the Sun and planets to adjust their orbits, potentially targeting specific destinations in the inner solar system. The mothership wouldn't need to slow down, it would just release its payload and continue outward, while the probes remain behind. We wouldn't detect this immediately because the probes would be small, faint, hard to see against the brightness of the comet itself during perihelion. But in the weeks and months after perihelion, as the probe's trajectories diverged from the mothership's path, we might start detecting them as separate objects moving on different orbits. This is speculation, of course, hypothesis without confirmation, but it's hypothesis grounded in the data, in the anomalies, in the patterns that suggest something unusual might be happening. Science is about considering possibilities, assigning probabilities, and then testing those possibilities with observations. The test happens in late October and early November. The observations resume in December when 3 Atlas becomes visible again from Earth, and then we'll know. Here's what the post-perihelion observation campaign will look like. Starting around November 27th and running through January 27th, the International Asteroid Warning Network is coordinating a dedicated campaign to track 3 Atlas. This is notable because IAWN typically focuses on potentially hazardous near-Earth asteroids, not interstellar comets that pose no threat to Earth. But they've made an exception for 3 Atlas, announcing on October 21st the exact date of solar conjunction that they're implementing a special comet astrometry campaign. The stated goal is to improve techniques for measuring cometary positions accurately despite the challenges posed by their diffuse comae and tails, but the timing is suggestive. The campaign begins almost immediately after perihelion, almost as if they're preparing to look for something unexpected. Multiple spacecraft will also observe. On November 4th, the European Space Agency's JUICE mission, currently en route to Jupiter, will pass within 64 million kilometers of 3 Atlas. JUICE carries cameras and spectrometers that can characterize the comet's composition and activity state. On December 19th, when 3 Atlas makes its closest approach to Earth at 269 million kilometers, every major observatory on the planet will likely be pointed at it. Then on March 16, 2026, as it passes 54 million kilometers from Jupiter, NASA's Juno spacecraft, currently orbiting Jupiter, will have the opportunity to observe it with instruments spanning ultraviolet to infrared to radio wavelengths. Juno can detect things that Earth-based telescopes can't, particularly magnetic fields and charged particle interactions. All of this observational coverage means we'll have an unprecedented dataset on an interstellar object's behavior as it transits through the inner solar system. If the trajectory remains purely gravitational, matching predictions, we'll confirm that 3 Atlas is a natural comet and close the book on speculation about artificial origin. The anomalies will remain unexplained, but will be filed under interesting cometary behavior that we don't fully understand yet, and research will continue to develop better models of cometary physics that can account for extreme carbon dioxide enrichment, unusual dust processing, and other observed characteristics. But if the trajectory deviates, if the velocity is wrong, if new objects appear, if there's any indication of non-gravitational maneuvering during the solar conjunction period, then everything changes. Then we have to seriously consider that 3 Atlas might be the first confirmed detection of extraterrestrial technology. Then we have to grapple with what that means for science, for society, for humanity's place in the cosmos. Loeb has been preparing for this possibility. The Galileo Project, which he founded and directs, is a scientific research program focused on searching for evidence of extraterrestrial technological artifacts, whether in the form of interstellar objects, unidentified aerial phenomena, or potential debris from advanced civilizations. The project operates observatories equipped with instruments designed to detect and characterize anomalous objects. Loeb has specifically tasked the Galileo project teams with monitoring for unusual activity near Earth in the coming months, looking for anything that might be related to 3 Atlas probes, debris, objects on unexpected trajectories, anything that doesn't fit the background noise of natural meteors and satellites and space junk. This is where we are. This is the moment. Late October 2025. 3. Atlas is behind the sun, unobservable, approaching perihelion. In the hum of observatories around the world, in the quiet rooms where astronomers analyze data and write code and prepare observation schedules, there's a sense of anticipation, of waiting to see what happens next, of knowing that within a few weeks we'll have our answer, or at least we'll have more data, more clues. More pieces of a puzzle that might ultimately tell us whether we're alone or whether something else is out there, capable of building machines that cross the void between stars. Let me tell you about the 33 billion tons, because that number keeps coming up and it's worth understanding what it means in concrete terms. 33 billion tons of mass, 33 trillion kilograms. That's roughly equivalent to the total mass of all humans currently alive, multiplied by 4,000. It's about the same as a cubic kilometer of rock, a mountain 1 kilometer on each side, lifted wholesale and thrown into space. For an interstellar object, it's enormous. Oumuamua was probably a few tens of thousands of tons at most. Borisov was maybe 100 million tons. 3 Atlas is 3 to 5 orders of magnitude more massive. That's not a small difference. That's the difference between a car and an aircraft carrier, between a house and a city. Why does this matter? Because mass is expensive. To eject an object from a planetary system requires energy. The larger the object, the more energy needed. The probability distribution of ejected objects heavily favors smaller ones because they require less energy to eject, and there are more of them to begin with. The fact that the 3rd interstellar object we've detected is so much more massive than the first 2 is statistically strange. It's like playing a lottery where small prizes are common and large prizes are rare, and your first 3 tickets win you $1, and then $1 million. Possible, but suspicious. Loeb calculates that based on the reservoir of heavy elements in the galaxy and the efficiency of planetary ejection processes, we should encounter interstellar objects on the scale of Oumuamua's size roughly once every few years with current detection capabilities. Objects on the scale of Borisov maybe once every decade or 2. But objects on the scale of 3 Atlas should be extraordinarily rare, perhaps 1 every 10,000 years or more. The fact that we've detected one after less than a decade of having the capability to detect interstellar objects at all is unlikely. It suggests either we've been incredibly lucky, or the population statistics are different than theory predicts. Or 3, Atlas isn't a randomly ejected object following the same distribution as the others. That last possibility is what Loeb keeps circling back to. If 3 Atlas didn't arrive here by random chance, if its trajectory and mass were chosen deliberately, then the statistics become less problematic. You don't need to explain why something so rare happened to show up so soon. It showed up because it was sent, directed, aimed at our solar system, specifically, rather than randomly wandering through the galaxy and happening to pass close to the sun by pure coincidence. This is where the alien technology hypothesis comes in. And it's worth being clear about what that hypothesis actually claims, because it's often misrepresented. Loeb is not claiming that 3 Atlas is a spacecraft piloted by living aliens who are coming to invade or contact us. He's not claiming little green men. What he's suggesting is the possibility that 3 Atlas could be an artificial object, a probe, a derelict spacecraft, a piece of technological debris, something manufactured by an intelligent civilization rather than naturally formed by accretion in a protoplanetary disk. It could be ancient, defunct, no longer under active control. It could be a von Neumann probe, a self-replicating machine sent out millions of years ago by a civilization that might no longer exist. It could be an artifact of unknown purpose, the equivalent of a message in a bottle thrown into the cosmic ocean, never expected to be found but discovered anyway. The key question isn't whether aliens are actively piloting it right now. The key question is whether it shows signs of being manufactured, of having properties that can't be explained by natural processes alone. Unusual mass to cross-section ratios suggesting artificial construction, orbital changes inconsistent with natural outgassing, emission of signals or objects, composition anomalies that make no sense for naturally formed bodies. These would be technological signatures, evidence of design and purpose, rather than random accumulation of ice and rock. And if it stays, if gravitational capture occurs, if the orbit changes from hyperbolic to elliptical, that would be perhaps the strongest technological signature possible. Because capture requires energy loss, and for an object this massive at this velocity, the only plausible mechanisms are artificial. Either a propulsion system actively braking, or some other means of shedding kinetic energy that we haven't thought of. Natural capture just doesn't work. The numbers don't allow it. So we wait. We watch. We prepare our instruments and our models and our minds for what December might bring. And we remember that this isn't the first time humanity has wondered whether something unusual in the sky might be more than it appears. 1953-57. The early Cold War years when every light in the sky was potentially an enemy aircraft or missile. The UFO wave of the 1950s and 60s, when people saw things they couldn't explain and feared invasion. We've been down this road before. We've looked for aliens in every anomaly, every unexplained phenomenon, every gap in our understanding, and every time, eventually, we've found natural explanations. Or we've found human explanations, misidentifications, hoaxes, psychological effects. We've never found aliens. Not once in all of human history have we confirmed the existence of extraterrestrial intelligence. But that doesn't mean they're not out there. Absence of evidence isn't evidence of absence, especially when we've barely begun to look. We've been conducting serious SETI efforts for about 60 years. We've examined maybe a few thousand star systems out of hundreds of billions in the galaxy. We've looked at a tiny fraction of the electromagnetic spectrum for a brief moment in cosmic time, with limited sensitivity. The fact that we haven't found a signal yet doesn't tell us much about whether signals exist. It just tells us we haven't found them yet with the methods and coverage we've employed so far. And here's the thing about interstellar objects. They're a different search space than radio SETI. Radio SETI looks for deliberate transmissions, beacon signals, civilizations that want to be found. Interstellar object searches look for physical artifacts, objects that might not be trying to communicate at all, but whose existence alone would prove that someone else is or was out there. An alien probe doesn't need to transmit a signal to be detected. It just needs to exist, to move through space, to reflect light or emit heat or occult stars or gravitationally perturb other objects. It's a passive search, in some sense. We're looking for the artifacts they left behind, rather than waiting for them to call us. If 3 Atlas turns out to be artificial, it would be the most important scientific discovery in human history. Not the discovery of life on other worlds. We might find microbial life on Mars or Europa or Enceladus someday. And that would be profound, but not entirely unexpected. No, this would be the discovery of intelligence, technology, engineering, evidence that minds other than ours have looked at the universe and decided to build things, to explore, to send their creations out into the dark. It would mean we're not alone. It would mean the vast silence of space is not the silence of emptiness, but the silence of civilizations, too distant to easily hear, too separated by light years and millennia to casually communicate, but present nonetheless, existing, thinking, building. And if it stays in our solar system, if it becomes captured, then it's not just passing through, it's here, with us. An artifact of another civilization taking up permanent residence in orbit around our Sunday. We could study it. In principle, we could send a spacecraft to rendezvous with it, to examine it up close, to touch it and sample it and understand what it's made of and how it was made and what purpose it was built to serve. That possibility is intoxicating to some researchers, terrifying to others, because if we can study it, what might we learn? About material science? About propulsion? About technologies that we haven't invented yet? And if it's still functional, if it's still active after billions of years of travel through interstellar space, what might it do? What was it programmed to do when it arrived at a planetary system with life and intelligence? This is where the dark forest hypothesis enters the conversation, and it's worth addressing because it's been mentioned in some of the more speculative papers about 3 Atlas. The dark forest hypothesis is a proposed solution to the Fermi paradox, the question of why, if intelligent life is common in the galaxy, we haven't detected any sign of it. The hypothesis, popularized by Liu Cixin's science fiction novel, The Dark Forest, suggests that civilizations remain silent because the universe is dangerous. Any civilization that reveals its location risks being targeted by more advanced civilizations that view newcomers as potential threats. So everyone stays quiet, hidden, lurking in the dark forest of the galaxy, hoping not to be noticed. And when they do detect another civilization, the safest strategy is to eliminate it before it can become a threat. In the context of 3 Atlas, the dark forest hypothesis would suggest that if the object is artificial and was sent here deliberately, it might not be friendly. It might be a scout, assessing whether our civilization is worth communicating with, trading with, or eliminating. Some of the more provocative papers written about 3 Atlas have explored this scenario explicitly, calculating what trajectory a hostile probe would follow if it wanted to survey the inner solar system while remaining hidden from Earth-based observation during critical maneuvers. And disturbingly, the trajectory of 3 Atlas fits those calculations remarkably well. The solar conjunction at perihelion, the close approaches to multiple planets, the retrograde orbit that allows rapid encounters. If you were designing a scout probe to survey the Sol system while minimizing detection risk, this is close to the optimal trajectory you'd choose. This is speculation piled on speculation, of course. It assumes not only that 3 Atlas is artificial, but also that it's hostile, and that the dark forest hypothesis is correct, all of which are unproven and arguably unlikely. Most researchers dismiss this scenario as science fiction rather than science. Loeb himself, while acknowledging the possibility, has emphasized repeatedly that the most likely outcome is that 3 Atlas is natural. He's not claiming certainty about artificial origin. He's not fear-mongering about alien invasion. What he's doing is pointing out that the data allows for multiple interpretations, and that one of those interpretations, however low probability, is technological origin. And if there's even a small chance of that, even a few %, then we need to take it seriously because the implications are so profound. So, let's talk about those implications. What happens if we confirm that 3 Atlas is artificial? What changes? First, scientifically, we would have proof of extraterrestrial intelligence. That single data point would revolutionize multiple fields. Astrobiology would shift from a largely theoretical discipline to an observational one, with a confirmed example to study rather than just models and speculation. SETI would be vindicated not in terms of radio signals, but in terms of the broader goal of detecting technosignatures. The equations we use to estimate the number of communicative civilizations in the galaxy, like the Drake equation, would gain a new constraint. we'd know that at least one other technological civilization existed at some point, somewhere, capable of building interstellar probes. Second, culturally and philosophically, humanity would have to confront the reality that we're not the universe's only thinkers. Every religion, every philosophy, every worldview has some assumption built into it about humanity's place in the cosmos. Some religions have already thought about this and have theologies that accommodate extraterrestrial intelligence. Others would need to adapt. Philosophies centered on human uniqueness would need to be revised. The knowledge that we're not alone would permeate art and literature and politics and everyday conversation. It would be inescapable. Within a generation, children would grow up never having lived in a world where humans were the only known intelligent species. That shift in perspective, in baseline assumptions about reality, would be as profound as the Copernican revolution that displaced Earth from the center of the universe, or the Darwinian revolution that connected humans to the rest of biology through evolution. Third, practically, we'd face decisions about what to do. If 3 Atlas is an artifact and it's in our solar system, do we try to communicate with it? Do we approach it physically? Do we ignore it and hope it goes away? These aren't purely scientific questions. They're questions that require input from governments, from international bodies, from people with expertise in diplomacy and ethics and risk assessment. There are existing frameworks for this, the SETI post-detection protocols, for instance, which outline recommended steps if we receive a confirmed signal from extraterrestrial intelligence. But those protocols were written with radio signals in mind, not physical objects in our solar system. We'd need to adapt them to figure out appropriate responses for this new situation. And if it does stay, if gravitational capture occurs and 3 Atlas settles into a long-term orbit around the Sun, then we'd have time. Years, decades, potentially centuries to study it before it fades away into the outer solar system or leaves entirely. We could plan missions, design spacecraft specifically to rendezvous with it, sample its surface, analyze its composition, search for markings or structures or anything that might tell us who built it and why. We could, potentially, learn from it. Reverse engineer its technology, if it has any technology to reverse engineer. Understand how it survived billions of years of travel through interstellar space exposed to radiation and micrometeorite impacts. Apply those lessons to our own spacecraft, our own attempts to reach other star systems. But all of this is premature. We're not there yet. Right now, in late October 2025, we're in the waiting period. The liminal space between observation campaigns. 3 Atlas is behind the Sun, hidden, unreachable by our telescopes. Whatever is happening right now at perihelion, we can't see it. We won't know until it emerges. Until the geometry changes and light from the comet can reach Earth again without being drowned out by the Sun's glare. In the silence of space, matter and energy follow physical laws. Trajectories curve according to gravitational potential. Velocities change according to applied forces. If 3 Atlas is natural, its trajectory is determined entirely by gravity and the rocket effect from outgassing. Those forces are calculable, predictable. We can model them with high accuracy. When we observe the comet again in December, its position and velocity will match those predictions, or they won't. That discrepancy, or lack thereof, will tell us what we need to know. If they match, we'll continue studying it as an interesting but natural interstellar comet, gathering data that will improve our understanding of cometary physics and the composition of icy bodies from other star systems. Papers will be written, careers will be built, knowledge will incrementally advance, and in a few years, 3 Atlas will fade from view as it climbs back out beyond Jupiter, beyond Saturn, eventually beyond Neptune and into the Kuiper Belt, and then past that into the scattered disk and finally into interstellar space, gone forever, A visitor that came and left and was seen by one generation of humans who happened to have telescopes pointed at the right patch of sky at the right time. If they don't match, if there's a discrepancy, then everything changes. Then we have to figure out what that discrepancy means. Is it non-gravitational acceleration from asymmetric outgassing? Is it tidal effects from the sun, somehow larger than predicted? Is it measurement error, systematic biases in the astrometry? Or is it propulsion, deliberate course correction, evidence of technology actively guiding the object's trajectory? Distinguishing between these possibilities will require careful analysis. Outgassing can be ruled out if the magnitude and direction of the acceleration don't match what we'd expect from the observed gas production. Tidal effects are calculable and tiny for an object this size. Measurement error can be assessed by comparing observations from multiple independent observatories using different instruments and techniques. If those natural explanations don't work, if the residuals remain unexplained by conventional physics, then we're left with unconventional explanations. And that's when things get interesting. Loeb has said, repeatedly, that science is guided by evidence, not by expectations. We expect 3 Atlas to be natural, because that's the simplest explanation. The explanation consistent with everything we've seen before. But expectations don't determine reality. Reality is what it is, independent of our preferences or assumptions. If the evidence points toward technological origin, then we need to follow that evidence, even if it's uncomfortable, even if it challenges our worldview, even if it forces us to accept something we weren't ready for. That's the essence of the scientific method. Make hypotheses, test them with observations, update your beliefs based on what you find. It's how we discovered that Earth isn't the center of the universe, that time and space are relative, that the universe is expanding, that quantum mechanics describes reality at small scales. Each of these discoveries violated intuition, contradicted common sense, seemed absurd when first proposed, but the evidence eventually became overwhelming, and we adjusted. We accepted the new reality and moved on to exploring its implications. If 3 Atlas turns out to be artificial, we'll adjust again. It will seem absurd at first. Many people won't believe it. There will be arguments, controversy, demands for more evidence, accusations of error or fraud or wishful thinking. That's healthy. That's how science works. Extraordinary claims require extraordinary evidence, and confirmation of extraterrestrial technology would be an extraordinary claim. The evidence would need to be rock solid, unambiguous, reproducible, confirmed by multiple independent teams. But if that evidence comes in, if the trajectory deviates in ways that can't be explained naturally, if objects are released that follow non-gravitational paths, if we detect signals or structures or anything that screams this was made, then eventually the evidence would become overwhelming, and we'd adjust. What would that adjustment look like? Probably not the way movies portray it. Probably not with mass panic or religious upheaval or immediate collapse of social order. Humans are adaptable. We've absorbed shocking revelations before and continued functioning. The public discourse would be intense for a while, months, maybe a year. Every news outlet would cover it constantly. Social media would be filled with speculation and conspiracy theories and arguments. But gradually, it would normalize. It would become part of the background knowledge that everyone carries, like knowing that the Earth orbits the Sun or that humans evolved from earlier primates. We teach it in schools. Yes, we found an artifact from another civilization in 2025. Here's what we learned from it. And life would go on. The scientific and technological implications would unfold over decades or longer. Understanding an alien artifact, if that's what 3 Atlas is, wouldn't happen quickly. It took us centuries to go from Newton's laws to quantum field theory, from the discovery of electricity to quantum computers. Reverse engineering technology from a civilization that might be millions or billions of years more advanced than us would be challenging, to put it mildly. We might not understand what we're looking at. The materials might be exotic. The engineering principle's unfamiliar. It could be like giving a smartphone to ancient Romans and asking them to explain how it works. They might recognize that it does things, that it responds to touch, that images appear on the surface. But understanding the integrated circuits, the software, the radio protocols, the satellite networks, that would require knowledge they don't have, frameworks they haven't developed, but we'd try. We'd send missions to study it. We'd use every instrument we have, every technique we've developed for analyzing materials and surfaces and compositions. We'd take samples if possible, bring them back to Earth for detailed lab analysis. We'd collaborate internationally because something this important transcends national boundaries. And slowly, over years and decades, we'd piece together what we could learn. Maybe we'd figure out what it's made of, how it was constructed, what power source it uses, whether it's still functional or dormant or defunct. Each answer would lead to new questions, new mysteries to investigate. The process might take centuries, but it would transform our technology, our capabilities, our understanding of what's possible. And if it's still active, if it does something after perihelion releases probes, transmits signals, maneuvers toward Earth or another planet, then the timeline accelerates. Then we'd need to respond faster, more carefully, because we'd be interacting with something intelligent, something with its own agenda, something that might have purposes we can't predict. That's where the real uncertainty lies, the deep unknown. An alien artifact following its programming might do anything. It might try to communicate, to establish a dialogue, to learn about us as we try to learn about it. Or it might simply continue its mission, whatever that mission was, indifferent to our presence. Or, in darker scenarios that most scientists consider unlikely but can't entirely rule out, it might assess us as a potential threat and respond accordingly. This is why Loeb has been urging careful monitoring. Why he tasked the Galileo project to watch for unusual objects near Earth in the coming months. Why he's been giving interviews, writing blog posts, making sure that people are paying attention. Not because he's certain that 3 Atlas is artificial, he's not. But because, if there's even a small chance, even 10 or 20 or 30%, then we need to be prepared. We need to have our instruments ready, our analysis frameworks prepared, our response protocols thought through. We need to not be caught completely off guard if something unexpected happens. October 29th is in the past now, or soon will be, depending on when you're reading this. By the time this documentary is released, perihelion will have occurred. 3 Atlas will have made its closest approach to the Sun, swung through that critical point where Oberth maneuvers are most efficient, passed through the period when it was hidden from Earth-based observation. Whatever was going to happen will have happened, but we won't know yet. We'll be in the waiting period, the gap between perihelion and the December reappearance, the weeks when we can't observe and can only anticipate. This is the hardest part in some ways. The not knowing, the uncertainty. It's easier when you have data, when you can measure and calculate and test hypotheses. The absence of data, the forced pause in observation, creates a vacuum that speculation rushes to fill. And speculation without data can go anywhere, can imagine anything. Alien motherships releasing probe swarms, natural comets following their predicted trajectories, everything in between. Until the observations resume, we won't know which speculation matches reality. But we'll know soon. December is not far off. The observation campaigns are planned. The telescopes are ready. And when 3 Atlas emerges from behind the Sun, becomes visible again in Earth's skies, we'll point every instrument we have at it. We'll measure its position to within fractions of an arcsecond. We'll determine its velocity to within meters per second. We'll compare those measurements to the predictions from gravitational models, and the discrepancy, or lack thereof, will tell us what we need to know. If the trajectory matches predictions, then 3 Atlas is almost certainly natural. The anomalies, the mass, the trajectory alignment, the timing, the chemical peculiarities will remain interesting, but won't rise to the level of evidence for artificial origin. They'll be filed away as unusual comet properties that we'll continue studying and eventually, hopefully, explain through improved models of cometary formation and evolution. Loeb's hypothesis of potential technology will be considered and rejected, at least for this object, and the search will continue with future interstellar visitors. If the trajectory doesn't match, if there's unexplained acceleration or deceleration, if the orbit has changed in ways that gravity alone can't account for, then we have to take the technological hypothesis seriously. Not as proven, proving artificial origin would require more than just trajectory anomalies. We'd need multiple independent lines of evidence: unusual composition, inconsistent with natural formation, detection of signals or emissions that suggest active systems, visual evidence of structure or manufacturing, something definitive. But trajectory deviation would be a strong signal, strong enough to warrant intensive follow-up, dedicated missions, international coordination. It would shift the probability estimates substantially, raising the chance of artificial origin from Loeb's current 30–40% to much higher, maybe 70 or 80% or more depending on the magnitude of the deviation. And if objects are released, if new things appear in the solar system that weren't there before, then we'd have our answer. Multiple objects on different trajectories originating from 3 Atlas would be extremely difficult to explain naturally. Comets can fragment, can break apart into pieces that follow slightly different paths, but those fragments stay close to the original trajectory, diverging slowly over time. If we saw objects that rapidly diverged onto substantially different orbits, especially if those orbits seemed to target specific destinations like Earth or Jupiter, that would be consistent with deliberate deployment of probes with their own propulsion. That would be, effectively, confirmation of technology. In the quiet hours of early morning, when observatories track objects across the sky, when computers compile data from sensors and cameras and spectrographs, there's a routine to it. Most of the objects are familiar: asteroids in known orbits, comets returning after decades or centuries, satellites put there by humans, debris from old missions. Occasionally, something new appears, gets catalogued, gets added to the database. Usually it's just another asteroid, another small rocky body following its gravitational path through the solar system, interesting to specialists but not remarkable to the broader scientific community. 3 Atlas is not routine. It hasn't been routine since the moment it was discovered and its hyperbolic trajectory was confirmed. Every observation, every spectrum, every image has been scrutinized by researchers around the world, analyzed for clues about its nature and origin. The data has been made publicly available within days or weeks of acquisition, posted to preprint servers and databases where anyone can access it. This is how modern astronomy works: open data, open collaboration, multiple teams analyzing the same observations from different perspectives, checking each other's work, proposing alternative interpretations. The result is a distributed, decentralized investigation. No single person or team controls the narrative or the conclusions. Loeb has been one of the most vocal researchers, and his willingness to consider unconventional hypotheses has made him a controversial figure. Some colleagues respect his openness to possibilities, others dismiss. Others criticize him for sensationalizing the object, for giving too much credence to low probability scenarios, for potentially damaging the reputation of serious SETI research by association with fringe speculation. The debates play out in papers, in blog posts, in conference presentations, in the peer review process. This is healthy. Science thrives on disagreement, on multiple perspectives, on people checking each other's calculations and pointing out flaws in reasoning. The fact that researchers disagree about 3 Atlas, that there's controversy about its interpretation, doesn't mean someone is wrong or lying or misguided. It means we're at the edge of knowledge, in territory where the data is ambiguous and multiple interpretations remain viable. As more data comes in, some interpretations will be ruled out and others will gain support. Eventually, if we're lucky, we'll converge on a consensus explanation that accounts for all the observations. But we're not there yet. What we have right now, in late October 2025, is uncertainty, multiple hypotheses, competing explanations, and a date on the calendar, December, when observations resume that will provide new data to test those hypotheses against. That's where we are. That's the state of knowledge. And it's okay to be uncertain, to not know, to admit that we're waiting for more information before drawing firm conclusions. But it's also okay to prepare, to think through scenarios, to consider possibilities even if they're unlikely. Because if one of those unlikely possibilities turns out to be correct, if 3 Atlas does something unexpected, we want to have thought about it in advance. We want to have frameworks ready for interpreting what we see, protocols for responding appropriately, coordination mechanisms for bringing together the expertise needed to understand something genuinely novel. This is what Loeb has been advocating for. Not certainty about alien technology, but preparedness for the possibility. Taking it seriously enough to think it through, to plan observations, to develop response strategies. Because the cost of preparation is low, some time, some telescope hours, some thought and analysis. But the cost of being unprepared if something extraordinary happens would be high. We'd waste time being surprised, arguing about what to do, scrambling to organize a response. Better to think it through now, while we're still in the waiting period, so we're ready for whatever December brings. Let me tell you about the green plasma haze that appeared during the lunar eclipse. September 7th, 2025, the moon passed into Earth's shadow, blocking the sun's light, creating a brief window of exceptionally dark skies. 2 astrophotographers in Namibia, Michael Yeager and Gerald Raymond, used the opportunity to image 3 Atlas with long exposures, capturing faint details that would normally be washed out by the moonlit sky. When they processed the images, combining multiple exposures through different color filters, they saw something unexpected. The comet, which had appeared reddish in earlier observations, now showed a distinct green coloration in the coma. Green comets are not unusual. The color typically comes from diatomic carbon, C2, molecules fluorescing in sunlight. But spectroscopic observations of 3 Atlas in August had shown little or no C2, suggesting the comet was depleted in carbon chains compared to typical comets. So where was the green light coming from? Loeb proposed that it might be cyanide, CN, which can also produce greenish emission under certain conditions. And indeed, the Very Large Telescope in Chile had detected cyanide in 3 Atlas's coma on August 21st, along with atomic nickel vapor, another unusual finding. The green coloration was transient. It appeared during the eclipse observation when conditions were optimal for detecting faint emissions, and then subsequent observations in brighter skies didn't clearly show it. This could mean it was always there but too faint to see except under the darkest conditions. Or it could mean the chemistry of the coma was changing, with production rates of different molecules varying as the comet's distance from the sun decreased and solar heating increased. Either way, it added to the list of unusual properties of things about 3 Atlas that don't quite match the standard comet profile. Nickel vapor is particularly intriguing. Metals like nickel have very high sublimation temperatures and shouldn't be present in gaseous form in a cometary coma at the temperatures and distances involved. The standard explanation is that nickel is being released not by sublimation of metallic nickel, but by photochemical breakdown of organic compounds or dust grains that contain nickel in molecular form. When solar ultraviolet light hits these compounds, it can liberate metal atoms, releasing them into the gas phase where they can be detected spectroscopically. But here's the puzzling part. Nickel was detected, but iron wasn't. In natural cosmic material, iron is generally about 10 times more abundant than nickel. They're usually found together because they're produced together in stellar nucleosynthesis and mixed together in the interstellar medium and in protoplanetary disks. If you find nickel, you should find iron, and you should find more iron than nickel, Yet the spectra of 3 Atlas showed strong nickel emission and no detectable iron. That's strange. It suggests either that the composition of the comet is unusual, with nickel enriched and iron depleted compared to cosmic abundances, or that the process releasing nickel into the gas is somehow selective, liberating nickel, but not iron. Loeb noted that this ratio, high nickel, low or absent iron, is characteristic of industrially produced nickel alloys used on Earth for corrosion-resistant coatings. That doesn't mean 3 Atlas is coated with industrial alloys. That would be absurd for a natural comet. But it does mean the elemental ratios are odd, not easily explained by standard cometary chemistry. It's another anomaly, another data point that doesn't quite fit. Taken individually, each of these chemical anomalies can probably be explained by some combination of unusual formation conditions, unusual parent body composition, or unusual processing during billions of years in interstellar space. Comets are diverse. Solar system comets show a range of compositions, and we've only studied a few dozen in detail. There's no reason interstellar comets should be identical to solar system comets. They formed in different environments, around different stars, with potentially different elemental abundances and different thermal histories. So finding an interstellar comet with unusual chemistry is not, in itself, evidence of anything other than the diversity of cometary bodies across the galaxy. But when you stack the chemical anomalies on top of the trajectory anomalies, the mass anomaly, the timing, all 8 points that Loeb enumerates, the cumulative picture starts to look less like natural diversity and more like something genuinely unusual. Each anomaly raises the probability slightly. Individually, they might only shift your assessment from 99% natural to 98%. But combined, 8 anomalies, each shifting the probability a few percent, that can add up to something significant. This is Bayesian reasoning. You start with a prior probability, your initial estimate of how likely something is before considering specific evidence. For the question, is this interstellar object artificial? The prior is very low, maybe 1 in a million or 1 in a billion, because we've never confirmed artificial interstellar objects before. Then you update based on evidence. Each anomaly that's more consistent with artificial origin than natural origin increases the posterior probability. If you're rigorous about it, if you assign actual numbers to how much more likely each piece of evidence is under the artificial hypothesis versus the natural hypothesis, you can calculate how much the probability shifts. Loeb's assessment of 30 to 40% probability for artificial origin implies that he thinks the combined evidence from all 8 anomalies is strong enough to shift the probability up from the negligible prior to something non-negligible. Other researchers would assign different numbers, different likelihoods to each piece of evidence, and would end up with different posterior probabilities. That's fine. That's how subjective Bayesian reasoning works. Different people can look at the same evidence and reasonably disagree about its implications because they weight the evidence differently or have different priors. The important thing is that the posterior probability isn't zero. Even skeptics who think artificial origin is extremely unlikely would probably admit that the probability is higher for 3 Atlas than for random space rocks, maybe 1 in 1,000 or 1 in 10,000 instead of 1 in a billion. That's still low enough that you'd bet on natural origin, but it's high enough that you'd pay attention, that you'd collect more data, that you'd be prepared for a surprise. And the key test is coming, the trajectory measurement in December. That single observation has the potential to shift probabilities dramatically in one direction or the other. If the trajectory matches predictions, the probability of artificial origin drops substantially, maybe back down to 1 in a million. If it doesn't match, if there's unexplained acceleration, the probability shoots up, maybe to 70 or 80% or higher. One observation, one measurement, will do more to resolve the question than all the speculation and analysis that's come before. That's the power of decisive tests. Not all observations are equally informative. Some just refine parameters. improve precision, add detail to what you already know. But some observations answer fundamental questions, resolve ambiguities, force you to accept or reject hypotheses. The December trajectory measurement will be one of those. It will tell us whether 3 Atlas is following gravity or whether something else is going on. And that answer will shape how we think about interstellar objects, about SETI, about our place in the cosmos. In the meantime, in this liminal space of uncertainty, we wait, we think, we imagine possibilities, we prepare instruments and analysis pipelines, we write papers and proposals. We explain to the public what's happening, what it might mean, why it matters. We do the work of science, which is not just measurement and calculation, but also communication and interpretation and debate. And we remember that this has happened before, in a sense. Oumuamua, the first interstellar object, was also controversial. Also showed anomalies, the unusual shape inferred from its light curve, the non-gravitational acceleration detected as it left the solar system, the lack of visible outgassing despite the acceleration. Loeb proposed that Oumuamua might be a light sail, an artificial structure pushed by radiation pressure. Most researchers disagreed, proposing various natural explanations involving outgassing of hydrogen or other volatiles. The debate was heated, sometimes acrimonious, but it was also productive. It forced people to think carefully about what interstellar objects could be, to develop better models, to consider edge cases and unusual possibilities. Now we have 3 Atlas, and the debate is happening again, with higher stakes because the anomalies are more numerous and more difficult to explain away. Maybe this time we'll get a definitive answer. Maybe the December observations will be unambiguous, leaving no room for doubt about whether the object is natural or artificial. Or maybe we'll end up with more ambiguity, more data that could be interpreted multiple ways, more arguments about what the evidence means. We'll see. We'll know soon. But here's what we know already. Regardless of what 3 Atlas turns out to be, we're living through a unique moment in human history. A moment when we've developed the technology to detect interstellar objects, to study them in detail, to gather data that can potentially answer the question of whether we're alone. Previous generations could only speculate. They could imagine aliens, write stories about them, search the skies with radio telescopes hoping for signals. But they couldn't detect physical artifacts from other civilizations because they didn't have the instruments, the survey coverage, the computational power to process the data. We do. For the first time in human history, we can find interstellar objects, track them, measure their properties, and make informed judgments about their nature. That capability is new, less than a decade old, dating from the discovery of Oumuamua in 2017. And it's getting better. The Vera C. Rubin Observatory, which will begin full operation soon, will find dozens or hundreds of interstellar objects over the coming decade. Each one will be an opportunity to learn something new, to test hypotheses, to refine our understanding. 3 Atlas is the third data point. 3 is not a large sample size. It's barely enough to begin identifying patterns, distinguishing what's typical from what's unusual. But it's 3 more than we had a decade ago. And each one teaches us something. Oumuamua taught us that interstellar objects can have unexpected properties, that not everything fits neatly into our categories of comet or asteroid. Borisov taught us that some interstellar objects do look like familiar comets, that the diversity of cometary bodies extends across interstellar space. 3 Atlas is teaching us. Well, we're still figuring that out. But it's teaching us that interstellar objects can be massive, that they can have unusual chemistry, that they can arrive on trajectories that seem improbably well aligned with our planetary system. What will the 4th interstellar object teach us? The 10th? The 100th? We'll find out. We'll accumulate data, build statistical samples, understand the population of objects drifting through the galaxy, and maybe, eventually, we'll find one that's unambiguously artificial. One that transmits signals, or has visible structure, or maneuvers in ways that natural objects absolutely cannot. When that happens, if that happens, we'll be ready. We'll have frameworks for analyzing it, protocols for responding, experience from having studied Oumuamua and Borisov, and 3, Atlas, and all the others that will be discovered in between. Or maybe we'll never find a confirmed artificial object. Maybe 3 Atlas will turn out to be natural, and so will the 4th and 10th and 100th interstellar visitor. Maybe the galaxy is full of civilizations, but they don't build probes that we can detect. Or maybe we're alone, or at least alone in our local region of the galaxy, the only intelligence within thousands of light years. That would be a different kind of profound, a different kind of lesson. It would mean the universe is ours to explore, with no one to guide us or teach us or compete with us. It would mean whatever future humanity builds is the only future intelligence builds in this corner of the cosmos. I don't know which possibility is more awe-inspiring. A universe filled with other minds, other civilizations, other explorers sending their artifacts across interstellar space. Or a universe where we're the first, the pioneers, the ones who will eventually send our artifacts out to drift among the stars. Both possibilities carry weight. Both change how you think about existence, about purpose, about what it means to be human in this vast cosmos. What I do know is that we're going to find out. Maybe not with 3 Atlas, maybe not in our lifetimes, but eventually, as we build better telescopes and detect more objects and explore more of the solar system and eventually venture to other stars ourselves, we are going to answer the question of whether we're alone. That answer, when it comes, will be one of the most important moments in human history. It will mark the point where we transition from wondering to knowing, from speculation to fact. And 3 Atlas might be part of that transition. It might be the object that forces us to take the question seriously, to move beyond casual speculation and actually prepare for what we'd do if we found evidence of extraterrestrial technology. Even if it turns out to be natural, even if the December observations show a perfectly gravitational trajectory and all the anomalies fade into the background as things we'll eventually explain, it will have served a purpose. It will have made us think, made us prepare, made us develop the tools and frameworks we'll need when the unambiguous case eventually arrives. Because it will arrive. The galaxy is vast, hundreds of billions of stars, trillions of planets. If even a tiny fraction of those planets develop technological civilizations, and if even a tiny fraction of those civilizations send out interstellar probes, then the galaxy should contain billions or trillions of artifacts drifting through interstellar space. Some of them will pass through our solar system. The question isn't whether we'll encounter artificial interstellar objects, assuming they exist at all. The question is when, and whether we'll recognize them when we see them. 3. Atlas has heightened our awareness, has made us look more carefully, has reminded us that not everything in space is what it first appears to be, that the universe can surprise us, that the categories we've built from limited experience might not encompass everything that's out there. That's a valuable lesson, even if this particular object turns out to be a comet. It keeps us humble, keeps us questioning, keeps us from becoming complacent in our assumptions. And if it's not a comet, if it's something more, then we'll deal with that. We'll gather more data, analyze it carefully, reach conclusions based on evidence rather than wishes or fears. We'll communicate internationally, coordinate observations, share data openly so everyone can verify the results. We'll be transparent about what we know and what we don't know, about the certainties and the uncertainties. We'll resist the temptation to jump to conclusions before the evidence is solid. And we'll prepare for a future that might be very different from the one we imagined. This is what it means to do science in real time, to work at the frontier of knowledge where questions outnumber answers. It's messy, it's uncertain. It involves false starts and dead ends, and hypotheses that seemed promising but turned out to be wrong. but it's also exhilarating. There's nothing quite like being at the edge, looking into the unknown, knowing that the next observation might change everything. We're at that edge now, late October 2025, 3 Atlas behind the Sunday December approaching. The observations waiting to be made, the data waiting to be analysed, the truth waiting to be revealed, whatever that truth turns out to be. And in the quiet of observatories around the world, in the hum of computers processing telemetry from space telescopes, in the minds of researchers thinking through scenarios and preparing for what comes next, there's a sense of anticipation, of holding our breath, of waiting for the moment when we'll know. Perhaps it was never passing through at all. Perhaps it came home. That's the possibility that won't go away. The thought that lingers even when you try to be rational and skeptical and evidence-based. What if 3 Atlas isn't a random visitor but a returning artifact? Something sent out long ago that's now coming back? Or something that was always meant to arrive here? Following a trajectory calculated millions of years in the past, timed to reach our solar system precisely when we'd be capable of detecting it? These are speculations. Fantasies, maybe. The evidence doesn't support them. Not yet, anyway. But they're the kind of thoughts you have when you're faced with something genuinely anomalous, something that doesn't fit your existing frameworks. Your mind reaches for explanations, even unlikely ones, because the alternative is accepting that you don't understand, that the universe has presented you with a mystery you can't yet solve. And that's okay. It's okay to not know. It's okay to wait for more data. It's okay to hold multiple possibilities in mind simultaneously, assigning them different probabilities, being prepared to update those probabilities as new evidence comes in. That's epistemic humility. That's acknowledging the limits of current knowledge while remaining open to whatever we learn next. In December, we'll learn more. The telescopes will track 3 Atlas across the sky. The astrometry will be reduced, the orbits recalculated. The comparison between observed and predicted trajectories will be made with high precision, and we'll see whether the numbers match or whether they don't. Whether gravity alone explains the motion, or whether something else has acted on the object during its passage through perihelion. That measurement will not be the end of the story. Even if the trajectory matches perfectly, questions will remain about the chemical anomalies, the mass, the alignment. Even if the trajectory doesn't match, we'll need to confirm it with additional observations, rule out systematic errors, determine the magnitude and direction of any non-gravitational acceleration. Science doesn't provide instant answers. It provides incremental progress, gradual refinement of understanding, asymptotic approach to truth. But the December observation will be a major step. It will tell us whether we need to seriously consider artificial origin or whether we can confidently rule it out. It will shape the research agenda for years to come, determining which hypotheses get pursued and which get set aside. It will, in a very real sense, determine how we think about 3 Atlas and what lessons we draw from it. So we wait. In the darkness, in the cold space between here and there, an object moves, massive and ancient, cold and distant, carrying within it or upon it clues to its nature and origin. It approaches the sun, feeling the star's warmth for the first time in billions of years. It outgasses, shedding material that's been frozen since before Earth existed. It falls along a trajectory determined by forces we can calculate or forces we can't yet understand. And we watch, with instruments that can detect light from across the universe, with telescopes that can resolve details smaller than the object itself if we could get close enough, with computers that process the data, fit models, calculate residuals, with minds that interpret, that question, that imagine possibilities. In a few weeks, we'll have our answer. Or at least, we'll have more data, more constraints, more pieces of the puzzle. And we'll keep watching, keep measuring, keep thinking about what it all means. Perhaps it was never passing through at all. Perhaps it came home. Or perhaps it's just a comet, ancient and strange, carrying ice and dust from another star system through our cosmic neighborhood on its way to somewhere else. Either way, we're here. We're watching. We're thinking about what it means, about what we've learned, about what we'll do with the knowledge we gain. And that, in itself, is extraordinary. The fact that we can have this conversation, the fact that we can detect interstellar objects and study them and debate their nature, the fact that we've developed, in just the last century, the technology to reach beyond our planet and look at the universe with instruments that extend our senses far beyond their biological limits. Our ancestors looked at the sky and saw mystery. We look at the sky and see mysteries we can investigate, questions we can answer, problems we can solve through observation and measurement and thought. That's the gift of science, the power of the scientific method. It takes the unknown and makes it knowable, takes the mysterious and makes it comprehensible, takes the distant and brings it within reach. 3 Atlas is distant still, tens of millions of kilometers away, moving fast, impossible to reach with current technology. But we can see it. We can measure its light, analyze its spectrum, track its motion. We can learn from it even though we can't touch it. And that's enough. For now, that's enough. In December, when the observations resume, we'll see what there is to see. We'll measure what there is to measure. We'll learn what there is to learn. And then we'll know whether to keep speculating about artificial origin or to set that hypothesis aside and focus on understanding 3 Atlas as a natural object with unusual but ultimately explainable properties. Until then, the question remains open. The possibility hangs in the air like the ghost of futures yet to be determined. And we wait, in the silence between observations, for the moment when data replaces speculation and we can move forward with confidence rather than wondering. The universe is vast, the questions are countless, the mysteries are deep. But we're here, asking and observing and thinking, and that means, eventually, we'll find answers. Maybe not all of them, maybe not quickly, but we'll find them. 1 observation at a time. 1 object at a time. 1 mystery at a time. Perhaps it was never passing through at all. Perhaps it came home